All right. This is section 7.2. All right. Let's take a polynomial, a rational polynomial expression. Section 8.2, thanks. Okay, so let's take a rational polynomial expression like, okay, state the domain. State the domain. What would the domain be? The domain is, I mean, really, can we use any value we want for x? Yes. Except 2. Can't divide by 0. So x cannot equal 2, because if you put in 2 for x, 2 minus 2 is 0. You can't divide by 0. So here's how we write your domain. It's called set builder notation. I can use all of x, colon, such that x cannot equal 2. Okay, it's called set builder notation. Sometimes you'll see it written this way. Sometimes you'll see it with a straight line like that. It just depends on the book. Okay, you can use it, and what it says essentially is that you can use all of x such that x cannot equal 2. Okay, it's the only one you can't use. Well, what happens if we graph that? What if I were to graph this thing? What happens at x equals 2? All right, well, let's just sort of sketch this. So that all up and down the graph, x cannot equal 2. So maybe this graph will look like, all right, as it approaches from the left, it can't cross it, and it can't touch it. And you know what that dotted line is called? I'm not sure if we had that or not before. Anybody know? This red dotted line is called a vertical asymptote. Have you heard that before? Vertical asymptote. And one of the properties of a vertical asymptote is that your graph cannot touch it, cannot cross it. And eventually, what happens when you approach from the left is that it gets closer and closer and closer to this vertical asymptote, never touching, never crossing. Over on the right side, you can use all positive values greater than 2. And that's what it might look like over on the right side. When it approaches from the right, it gets closer and closer to the vertical asymptote, but it will never touch, it will never cross, because x cannot equal that. Vertical asymptote. Yeah?
So can it not cross the x-axis?
We'll talk about that one in a minute. We'll talk about the x-axis in a minute. Sometimes they do, sometimes they don't. But in this particular case, they do not cross the x-axis. Okay? All right. Vertical asymptote. And we can say our vertical asymptote is at x equals 2. Okay? Let's take another polynomial expression. I don't know, we'll call it p of x. And let's say x squared plus, let's make this 2x squared plus 3x minus 8 over x squared plus 2x minus 3. Let's find any vertical asymptotes. And while we're talking, let's find horizontal asymptotes as well. So first of all, the vertical asymptotes. It's the same as your domain. What can x not equal? Well, whatever makes your denominator equal to 0, you can't use. So let's factor the bottom. Remember I said there's going to be a lot of factoring in this chapter. So if I factor the denominator, x, let's see, x plus 3, x minus 1. How did you know it was 1? Okay, very good. All right, so really there are two vertical asymptotes here. And one is going to be at -3, and one is going to be at 1. Now they have you graphing as part of your homework, and all you really have to do is sketch it like I'm sketching on the board. All right, well, let's take this asymptote. I'm not sure what this looks like, but it might be something like here on the left. Maybe in between the two asymptotes, it'll look like that. And maybe over on the right side, it might look like that. Okay? So we can say our vertical asymptotes here are at x equals -3 and x equals 1. And those are the two vertical asymptotes. Okay? Horizontal asymptote. And this is where you need to read the book. And I think it's on page 492 in the blue box right in the middle of the page. It's going to explain what I'm going to explain right now. If the degree, we're looking at degrees. This is for horizontal asymptote only. If the degree of the numerator, let's take this first equation here. If the degree of the numerator is less than the degree of the denominator, the degree on top is 0. The degree on the bottom is 2. The degree is less on top than it is on the bottom. Then your horizontal asymptote is at 0. So Michelle, when you asked the question before, for this particular drawing, the horizontal asymptote is at 0. So it does not cross the x-axis.
How is the degree on the denominator?
The degree on the denominator is 1. Did I say 2? I'm sorry, I meant 1. The degree on the bottom is 1. The degree on top is 0. Okay? If the degree is less on top, y equals 0 is your horizontal. Now, and I will tell you, for a horizontal asymptote, that drawing is going to approach that at some point, but it can cross a horizontal asymptote. There is cases where it can cross a horizontal asymptote. Never vertical, but it could cross a horizontal one. In the second example I gave you, if the degree of the numerator is the same as the degree of the denominator, here the two degrees are the same, you look at the leading coefficients, and we see that it's 2 over 1. 1x squared, right? And so your horizontal asymptote is y equals 2. You're just looking at the coefficients. And if you check out what I did here, you can kind of see that this is raised up a little bit. I did that on purpose. All right? Any questions? So we have vertical asymptotes that we can get from your domain, from your denominator. You get the horizontal asymptotes by looking at, if the degrees are the same, you look at the coefficients. If the degree is less on top, then y equals 0. It follows along the x-axis. If the degree is greater on top, maybe you'll have an equation that looks like y equals, I don't know, maybe x cubed minus 2x over 3x squared plus 7. If the degree of the numerator is greater than the degree of the denominator, then there is no horizontal asymptote. If the degree is greater on top than it is on the bottom, then there is no horizontal asymptote. And those are the three rules. Less on top, y equals 0. If it's the same, you look at the leading coefficients. If it's greater on top, then there's no horizontal asymptote. Is that clear so far? All right. So, here's a problem. Let's say we have a polynomial. And let's say we have x squared plus 5x minus 6 over x squared, let's do the one we did before, plus 2x minus 3. The directions will say, list all vertical and horizontal asymptotes and any holes in the graph. Holes in the graph. We haven't had that yet. All right, let's check that out. All right. And we're going to sketch the graph. Well, if I factor the denominator, I've got x, we did this one before, x plus 3, x minus 2, or x minus 1. My domain, you cannot use negative 3 or 1, are they vertical asymptotes? You can't tell just yet because I'm going to factor the top. And if you factor the numerator, you're going to get x plus 6, x minus 1, over factor the denominator, x plus 3, x minus 1. Okay? If something reduces, then we have a hole in the graph at x equals 1. I'll show you what that looks like in a minute. We have a vertical asymptote at x equals negative 3. Here's your vertical asymptote, x equals negative 3. There's a hole in the graph. The reason there's a hole in the graph is because it reduces with something on top. So there's a hole in the graph. It's not a vertical asymptote. And then, what is your horizontal? Well, that's going to be y equals, tell me, y equals what? 1. The degree is the same, so we're looking at the coefficients. 1x squared over 1x squared, 1 over 1 is 1. Here's what this might look like then. Here's your vertical asymptote at negative 3. Here's your horizontal asymptote at 1. I'm going to graph this on the screen to show you what it looks like. I've already got that programmed in my calculator, and that's what it looks like. So you see on the left side, okay? And if you look at the right of that vertical asymptote, it comes down like this, but what you don't see on the screen is that when it hits to the point where x equals 1, there's a hole, and then it continues on. And even though it doesn't show up in the screen, I know there's a hole at 1 because it reduced to something in the numerator. And if I were to trace, I can't really get to 1 on my trace unless I just put in 1 for x. And you can see that my calculator doesn't give me a value for y, because there is no value for y, because I can't use 1. Even though it doesn't show up on the graph, it's one of my domain restrictions. Not a vertical asymptote in this case. There's a hole in the graph because it reduced something on top. Does that make sense? I've got you reading. It seems like in this section there's a lot of information. So we have vertical asymptotes, horizontal asymptotes, holes in graph. Now you've seen all the examples I've given you on polynomials, rational polynomial functions. In the first section of your homework, if you see something that's different, if you see absolute value, that is not a rational polynomial. If you see something where x to the 2/3 power, that is not a rational polynomial. If you see anything different, where maybe we have 3 raised to the x power, that is not a rational polynomial. Anything that looks different than what we've done, it is not a rational polynomial. Okay, Mark? Yes?
So holes in the graph will always be at 1?
No. Holes in the graph will be it if one of these reduces, if something in the denominator reduces with something in the numerator. Maybe the x plus 3s would have reduced with something up here, but it didn't. So we could have a hole at -3, or holes can appear anywhere. As long as one of the factors on the bottom reduces with one of the factors on top, that's where the hole is. Is that clear? All right. I want you guys to take as much time as you can to get a few problems. Yeah, Michelle.
What if on the numerator it was like x plus 1 and it's just that?
No, it doesn't reduce then. If you have x minus 1 on top, x plus 1 at the bottom, that does not reduce. It has to be exactly the same. Your homework, I've got it written up on the board, is to read pages 489 to 494 and do problems 12 through 40 even, and 2-story problems 44 and 45. Problem number 44, an example of problem number 44 is in your reading. Okay, I don't see the need to go for that. Right? And that's your lesson.